So let's say you have a ball rolling down a ramp. So let's draw this out. So we have a ramp and there's this angle theta here. And then you have a ball on this ramp. And we're going to give this ball a mass big M and a radius big R that is rolling smoothly down the ramp along the x-axis. This is the positive x-axis here. We want to find an expression for this ball's acceleration, A, of the center of mass in the x direction down the ramp. So what is that value, right? And we can do this by using Newton's second law in both its linear version, which we know is F net equals ma, and its rotational or angular version, which we know is T net equals I times the angular acceleration alpha. We can start by decomposing the net force on this ball into its component forces. We know that there is always going to be a gravitational force here, and it is directed downward here. And it has components mg sine theta and mg cosine theta in the y and x directions, respectively. And we also have a normal force, Fn, that is pointing perpendicular to the ramp, like so. And it acts at the point of contact P, but we're going to shift this vector along its direction until its tail is at the body center of mass. So this is the point P that we were talking about. And then we also have a static friction force at the point of contact P. So in order to figure out which direction the static friction is pointing, let's consider if this ball were to slide at point P. If it were to slide, we know that it would be sliding downwards. So that means that the frictional force must be opposing the sliding motion. So the frictional force must point up the ramp, like so. And it's going to be a static frictional force because it's rolling smoothly, so it's not slipping at the point of contact, which means that the frictional force we're going to be using is the static frictional force. And with this, we can write Newton's second law for the force components along the x-axis, where F net in the x direction is equal to the force of static friction minus mg, but we're going to use sine of theta because we have decomposed the force of gravity, and this equals the mass times the acceleration of the center of mass in the x direction. And this equation contains two unknowns. We don't know the static friction and we don't know the acceleration of the center of mass. And now we can apply Newton's second law in its angular form to the ball's rotation about its center of mass. So we're going to use the equation that we have over here. And we know that T net is also equal to the perpendicular radial component times the net force in that direction. And the only force that is applying a torque to the body is the frictional force. And we know that because both the gravitational and normal forces have zero moment arms about the center of mass. So they produce no torque, obviously. So only the frictional force applies a torque, and it has a moment arm of R. So this is the torque that it provides. And then using the equation that we had above, this equals the rotational inertia at the center of mass times the angular acceleration. And because the body is rolling smoothly, we can use the relationship we have between the linear and angular accelerations. So we know that because it is rolling smoothly, we know that the acceleration of the center of mass is equal to the angular acceleration times the radius of the ball. And this lets us relate the unknowns of the linear acceleration and the angular acceleration. However, here we have to be careful with the signs because the acceleration of the center of mass is negative because it's in the negative direction of the x-axis here. This is the negative x-axis. But the angular acceleration is positive because we are moving counterclockwise. So we need to substitute the angular acceleration equals the negative linear acceleration of the center of mass divided by r. And we can substitute that into the equation that we got for the torque, and then we can solve for the static frictional force. So let's first apply the torque here. T net equals the force of friction times the times r, and this equals the I center of mass times the angular acceleration, which we have related to the linear acceleration like so. And now if we substitute and solve for the static frictional force, we get the static frictional force is equal to ICM times the linear acceleration of the center of mass in the x direction divided by r squared. Okay, and now we can substitute the value or the expression for the static frictional force into the Newton's second law equation that we found for the translational motion over here. And then we're going to get that MACM equals negative ICM ACM over r squared, because this is simply the f of s, and then minus mg sine of theta. And then if we rearrange and do some more algebra, you will find that the acceleration of the center of mass is equal to negative g sine theta divided by 1 plus the rotational inertia about the center of mass divided by mr squared. And that is how we can find the linear acceleration of any body rolling along an incline of an angle theta with a horizontal, not only for like a ball, for example. So now we're going to apply what we have learned to an actual problem. So let's assume that we are working with a ball rolling down the ramp in this example. So we're given that its mass is 6 kilograms. It has a radius r, which we don't know, and it rolls down from rest down a ramp of an angle 30 degrees. Okay. So the first part of this problem asks that if the ball descends a vertical height h is equal to 1.2 meters, then what is the speed of the ball at the bottom? Okay, so to do this, we're going to use the conservation of mechanical energy E of the ball and earth system as it rolls down the ramp. So the energy is conserved because the only force doing work on the ball is the gravitational force, and this is a conservative force. The normal force does zero work because it's perpendicular, and the frictional force doesn't transfer energy because the ball doesn't slide, as we're assuming that it rolls smoothly. So we can conserve mechanical energy using the equation K initial plus the potential energy initially equals K final plus U final. And we know that K initial is 0 because it starts from rest, and U final we're going to assume is 0 because we're going to take the reference point as the ground level where the ball will end up. So now this gives us a much more simplified equation, and we can rewrite this as mgh equals K final. And we know that K final has both translational and rotational parts. So we're going to decompose the kinetic energy into those two components, into its translational part, which is 1/2 mvcm squared, and the rotational part, which is 1/2 ICM times the angular speed. Okay, And because the ball rolls smoothly, we know that the angular speed is equal to the linear speed divided by the radius. This is a relationship that works for any smooth rolling motion. And we can substitute this into the equation for the conservation of mechanical energy that we had. And we're going to get 1/2 mvcm squared plus 1/2 ICM times VCM squared over R squared. But we also know that ICM is simply just some constant value times MR squared. So we're going to rewrite ICM as so. And after rewriting that, we get 1/2. We're going to name that constant some constant beta times MR squared VCM squared over R squared. And if we look at that, the R squared simply cancels out, and we are left with something like so. And we can move the 1/2 m outside, and we get something like this. All right. Now, both the m's, I'm going to rewrite mgh here to make it a little bit easier. So the m's cancel out, and we're left with 2gh equals, we're going to bring the VCM squared out, VCM squared times 1 plus beta. And now if we want to solve for VCM, we get that VCM equals the square root of 2gh over 1 plus beta. And that is the square root of that. And beta here is just for a solid sphere. That is 2.2 over 5, because the rotational inertia of a solid sphere is 2 over 5 mr squared. And this value over here is the beta. And if we plug in all the values, we will get that VCM equals 2 times 9.8 meters per second squared times h, which is 1.2 meters, divided by 1 plus 2 over 5. And if we take the square root of this entire thing, we get VCM is equal to 4.1 meters per second. Now, the second part of this question asks us what the magnitude of the frictional force on the ball is. So we just found out that the acceleration of the center of mass can be written as this equation here. And based on what we just saw, this simplifies to beta, and for a solid sphere, beta is just equal to 2 over 5. So we can rewrite this as negative g sine theta over 1 plus 2 over 5. And plugging things in, we'll get that the acceleration of the center of mass is equal to negative 9.8 meters per second squared, sine of 30 degrees, which is the angle between the ramp and the horizontal, over 1 plus 2 over 5. And this gives us the acceleration of the center of mass is equal to negative 3.5 meters per second squared. And note also that we didn't need either the mass or the radius to find the acceleration. So this tells us that any size ball with any uniform mass would have the exact same rolling acceleration if it were rolling smoothly down a 30-degree ramp, which is pretty cool if you think about it. So now we can use the acceleration of the center of mass to solve for the static frictional force. We know that static frictional force is equal to the negative rotational inertia about the center of mass times ACM divided by R squared. This was the relationship we found when we were deriving these equations. And we know that ICM is simply 2 over 5 R squared times ACM over R squared. The R's cancel out, and we get that the static frictional force is 8.4 newtons. So I hope you guys have found this video useful for solving questions about rolling objects down a ramp. These will be very prominent and common problems in the future, and I hope you guys have learned something new. I hope you guys come back for the next video, and I'll see you guys next time.